I just want to thank Lockheed Martin again for their sponsorship of the series. So today's speaker is Dr. Nikolai Astanasa. He is an assistant professor from the University of California, San Diego in the Department of Electrical Computer Engineering. He's really new there. Very cool. He got his PhD, did a postdoc at Penn, and he works in controls, robotics theory, and machine learning and the intersection of that, and information collecting on autonomous ground vehicles and aerial vehicles, and so he'll talk about that.
Thank you very much. Thank you everyone for coming, and it's a great pleasure to be here. I'm very excited about this opportunity to share my work and ideas with you. So I work in robotics, and my main focus is on active perception. So I'm going to tell you a bit about my work in autonomous exploration and mapping, and how we connect this with visual and semantic information. So I'm motivated by some of these advances in robotics. We've seen in recent years a lot of success in computer vision, and particularly in recognizing objects out in the wild, in 2D and 3D, and even estimating higher order information such as orientation of objects, maybe even tracking dynamic objects and doing segmentation. So there's a lot of exciting progress in kind of low-level perception, I would say. And it's a similar situation if we look at the control side. So we've seen a lot of progress on things like robust walking, maybe a robot driving a car or getting out of a car. So this is an example of JPL's entry into the DARPA Robotics Challenge. And there are several other very impressive achievements in control theory, or kind of legged locomotion, or very aggressive flight maneuvers, or dexterous manipulation. So to me, these are very promising results, but they are also kind of on the, I'd say, on the low level. We can now do some simple control tasks. We can do some low-level perception. So I think the big challenge, the big next step would be to capitalize on these control and perception advances and think about a higher level of autonomy. What can we use these robots for? So I'm very excited about problems in which robots are used to collect information. So examples of that might be, as I mentioned earlier, adaptive or active perception. So if you're interested in learning about a scene, you don't just look at it, but you're trying to see what you want to know about. Or other applications are environmental monitoring or precision agriculture, security and surveillance. So any application in which your robot is not just stationary, but wants to actively move around and learn about the things that are of interest. So let me make this a bit more precise and tell you kind of the class of problems that I'm excited about. So let's take as an example a problem of source seeking. So we could have for example, let's say there were a gas leak in a building and we don't want to send a human inside. We could deploy a robot to detect where this gas leak is coming from. And I wanted to just think about what are the components in such a problem and how can we achieve such a thing. So the first thing we need to understand is kind of what is our robot. So we need to have a good sense of the dynamics or the motion model of the robot, because ultimately we want to control the robot in a way that collects information for us. Second thing we need to understand is kind of what exactly are we looking for. So is it so if it's a gas leak, what do we know about the propagation of gas, or the kind of the detection or localization, or if it was let's say a person or an object that we're looking for. I think kind of understanding the dynamics of this target is also important. And then a third important model is kind of your measurement. So how does the state of your robot and the state of the target correlate to give you your observations? So depending on where you are in the environment and where the object is that you're looking for, you might receive different kinds of observations. Maybe there's an occlusion in front of your camera. Maybe there's an obstacle in the line of sight of your radio signal, which would affect the types of measurements you get. So based on these, if you understand these models well, then the next thing you want to do is kind of have a way of estimating where the target is just given measurements. Even if you don't move as you're receiving these measurements, you need to have a way of estimating the target state. And then finally, the interesting part is also how do you generate the motion of the robot in a way that it would improve the performance of such an estimator. So potentially there is some measure of uncertainty or of information in your understanding of this target or process of interest which you want to optimize. And then if we want to go even broader, potentially there might be multiple targets and multiple robots and they collaborate with each other. So then we get into things like how do you do this whole process in a distributed way? How do you do distributed estimation? How do you do distributed control? So this is starting to get very broad, but this is kind of the class of problems that I'm very excited about. So kind of to summarize the previous slide, I think the things we need to be able to do in order to solve such problems are first we need to choose representations for the targets, the robots, and the sensors. Either learn those or specify by hand or get them from somewhere. Then we need to design an inference algorithm which is able to take these models and infer what the target states might be. And then finally, there's a control problem which is trying to optimize the performance of the inference algorithm. So if we wanted to write this down as an optimization problem, potentially it's something like this. I have n robots and I have a finite time to plan my motion, and I'm interested in maximizing the information. So let's call some function j here, which represents the information, and that relates my robot's trajectory to the target's trajectory and to the types of measurements I obtain over time. So this whole problem is subject to constraints that come from these models. So examples of quantifying information are usually good examples come from information theory. So cost functions like mutual information, entropy, and probability of error are of interest to me. And then the constraints are from the models of the robot. So how does the robot move? How does the target evolve? What kind of measurements I obtain? Okay, so before even understanding the control problem, again, I think it's important to know how the inference process works, because that's then optimizing the performance of the inference really depends on how well you understand that process. So in a big part of my work, I actually focused more on the estimation part and wanted to see how can we model the world around us before we try to optimize this. So here's an example of the state-of-the-art in localization and mapping. So on the bottom left is a camera and an IMU together moving around in an environment, and the task is to estimate the trajectory of this sensor over time. So these green points that you see here are visual features, things like corners in the environment that you can reliably track, and this combined with the inertial measurements can give you a very good estimate of the trajectory of the camera and the IMU. And if you can do this well, you can also produce geometric map of the environment. Potentially, if you have a depth camera as well, you can start to map surfaces around you and colors and so on. But if you kind of pay attention to this, it's clear that most of the state-of-the-art is using only geometric information. So we have kind of ranges and bearings and planes and distances and lines and surfaces, but not really any object understanding here. And I told you a couple of slides ago that in vision we've had a lot of exciting progress. So in my work I've been very excited to bring some of the advances in vision into the localization and mapping work. So I've been, so in robotics we have very interesting approaches to doing this geometric localization and mapping. In vision we have very impressive ways of doing object detection, but not really localizing or estimating the poses and the locations of the objects. So I've been interested in building maps that combine positions, orientations, as well as semantic information about the objects, maybe potentially also moving things and just enriching this representation as much as possible. So this video on the bottom is showing the Kitty data set, for those of you who are familiar. It's a car driving through Karlsruhe in Germany and obtaining information from an RGB camera, a LiDAR, and an IMU sensor. So using this information, can we estimate the trajectory of the car over time, but also can we build a map, maybe not of the geometry, but of objects in the environment, in this example, cars in the environment. So I'm going to tell you a little more about how we might be able to do that. So the problem I'm interested in is kind of this unified formulation of localization and mapping, in which I have two sources of information. I have metric information coming from the visual features and the inertial measurements, and there's also semantic information coming from object detections, and maybe something lower level like object parts. For example, a car could have like wheels and windshield and doors, or segmentation. How does the object appear on a 2D image? Given all this information, I'm interested in kind of maximizing the likelihood of these measurements given the sensor trajectory and the landmarks in the environment, or the objects that generated these measurements. So in order to solve such an optimization problem, it's also important to think about data association. So what is that? That's kind of the correspondence between the measurements you get over time and the objects that are there in the environment. So let me make this more specific. So as an input, we assume that we have the geometric features. So here's, again, another example. We have an image. We can detect geometric features on this, which could be Harris-Korn, SIFT, SURF, and all the other three-letter abbreviations that were popular in vision before deep networks. And we also have linear acceleration and angular velocity from an IMU. So this is kind of the minimum sensing you need, a single camera and an IMU. In addition to this, we maybe have semantic information, which is in the form of object detection. So we can use a convolutional network to detect objects of different classes, and as I mentioned, potentially even extract semantic features. So these could be, again, parts of objects that are associated across different classes, so across different instances within the same class. So if I detect two different cars, I might be able to associate that this is the wheel of the car and this is the windshield or the door of the car. So we're interested in using these detections and the red key point, the semantic key points, to try to estimate the positions and orientations and the classes of the objects in the environment. So what is the output that we want? So ideally, I want to have an estimate of how did the sensor travel over time, what was the position, orientation, maybe velocity and acceleration and so on, and where are the objects, what classes are they, and how are they oriented in space. And as I mentioned, in order to do this well, there's this data association problem, which usually gets a little bit hidden under the rug, but you need to understand kind of what observation was generated by what landmark at a given time, and usually this information is also unknown. So if you make a mistake in this, your map might all of a sudden go very different from what you expect. So here's an example. Let's say you're observing an image in which there's two doors and a chair. There might even be potentially wrong detections. So there's a cabinet that looks like a door. And in your map, if you look at your map, there are many doors and many potential chairs. So the data association problem is which door did I actually see? If you're kind of uncertain about where you are and you're uncertain about what the environment looks like, you can never answer this with 100%, yes, this is the right door, or no, this is not the door I've seen. So there's some ambiguity in which door and which chair and which object I'm actually seeing. And if you make a mistake in this association, then you introduce this kind of wrong constraint in your optimization problem, and your map might end up looking like a pretzel. So it's important to not make hard decisions with data association. However, if we look at the kind of the state of the art in localization and mapping, we have exactly hard decisions when it comes to data association. So the usual approach to solving this optimization problem is to first, given the measurements and some initial guess of what your sensor trajectory was and what the environment looks like, the first step is to maximize the likelihood over the data associations. So do something like some kind of a gating test or something like the Hungarian algorithm to tell you what are the most likely associations between what I saw and what is on my map. And given this information, then you commit to these associations, and then you solve the optimization problem, which will then estimate the sensor trajectory and the object positions. And as I said, I don't think it's a good idea to make hard decisions. So if we if we look at this problem more carefully, it looks a little bit like coordinate descent. We have an optimization that's joint over several variables. We want to maximize over x, l, and d. And what does coordinate descent do? You fix one of the variables, optimize over the other ones. Then you fix the other ones, optimize over the first one. But there are better ways of doing this. How can we do joint optimization here? Well, really, the data association is something that I don't care about in the end. I want to build a map. I want to know where I am. I don't really care in the end which object was produced by which object. So one thing to do is to actually marginalize this unknown variable out and do something like maximize the expectation over the data association. So this would mean something like, can we estimate distributions over the possible associations, and can we compute these expectations? So the reason why a lot of the existing work doesn't focus on this is that actually estimating such a distribution is computationally very challenging. But we have some ways of doing this efficiently, or at least we've shown some interesting results in this regard. So our main result, what we were able to show in the localization and mapping problem, is that if we assume that this data association is probabilistic, we have not made any hard decisions about which observations associate with which objects, we can split this expectation maximization problem essentially using the EM algorithm. We can split it into two steps. The E step is something like the E step is understand the distribution over these assignments. How likely is it that this door was that door versus this door versus this door? Can we keep a distribution over this? And given such a distribution, then we can do an optimization over the object positions and object locations and the sensor position and orientation, which ends up being something like a nonlinear least squares problem. So the right-hand side is a little more the standard approach in SLAM. Yes?
What are you assuming about D? Because if D is semantic data, at least my initial impression is that it's not smooth, that it has no real structure.
Yes, so that's a...
Expected value even meaningful?
Yes, so that's a very good question. So what is D? So I'll actually give some more examples, but let me give you an exact definition. So we're assuming that D is a collection of functions over time, which at time t is telling you, so let's say at time t you have 5 observations and there's 100 objects in your map. It's giving you a mapping from the set of observations to the set of objects in the map. So for object 1, it's telling you this, for observation 1 is actually object 59, and observation 2 is object 13, and at every time step you might have a different function like this. So it's a function from sets to sets.
And those functions have an expected value that makes sense?
Yes, so you can have a distribution over the function and then have an expected value over this. So the question is, how do you actually compute this thing, right? Because this is a combinatorial thing. So I'll get into more details.
Combinatorial nightmare.
Yes, exactly, yes. So let's get into more details. So here's a little more details on in the E step of our problem. So we're interested in kind of deciding what is the likelihood of associating an observation K to landmark J, okay? So if I have, again, let's look at this example. I guess now, let's say there's 2 chair, 2 door observations, and then around my sensor, there's 2 doors and 1 chair. So given that observation K is associated with landmark J, I still have some uncertainty over how the other objects are associated. So how do I quantify this distribution, as you're saying, and is it even well posed to compute expectations over this? So let's think about this as kind of a graph, actually. So we have 3 observations there and 2 landmarks. And then if we think of it as a bipartite graph, then the data association is really some kind of matchings in this graph. So I have one way of assigning the observations to the landmarks, or a different way of assigning to the observations to the landmarks, or a third way of assigning them. And each of these matchings has a certain weight. So the weight for the matching is given by something like, if I were to assign this observation to be that door, how likely is this? So given your camera model, for example, and the projective equations, you can calculate some likelihood of the assignment based on the geometry. So we have different matchings in the graph, and they have different weights. Okay, so the data association is then really the correct data association is one of these possible matchings, and if we don't know which one it is, we have some kind of a weighted sum over all these different matchings. So if we're doing the expectation, so let me make this even more precise. So we can. So what happens if just a side note? What happens if the visible objects are not the same number as the observed objects? Then we might need to think about things like models for false detections and or missed detections or clutter. So you might have something that looks like a door produce a measurement even though it wasn't there. So in general, it would be an unbalanced bipartite graph, but you can introduce extra nodes to account for clutter, for example. So the specific equation is like the probability of observation K came from landmark J is something like the sum over all the other possible associations, and each of them has a weight. But given the association, the observations are independent because we know which object generated which observation. So given the association, we can assume that these are independent. So this term here, the likelihood of observation K being generated from landmark J, ends up looking something like the sum over the possible assignments times the product over the object likelihoods. And if we look at it from the graph point of view, it's the sum over all perfect matchings in a bipartite graph. So how do we actually compute this? So it turns out that computing weighted matchings in a graph, we can actually relate to an object called permanent. So if we take the adjacency matrix of this bipartite graph, and we compute the matrix permanent of this, it actually turns out that this is computing exactly the sum of all these weighted matchings in the graph. So if we look at the definition, if you haven't seen a permanent before, it's something like the determinant, but in your the cofactors appear with all with positive signs. So here's an example of a permanent. So we have kind of the observations on one side, the visible objects on the other side, and we can do something like, it's exactly like computing determinants, but now everything is with a positive sign. So if we add all these together, this would give us kind of an expectation over all the possible associations. So now instead of committing to one that's, okay, this is the most likely observation, we're computing all possible assignments and averaging over them. So computing permanence, so we kind of have shown that the unknown data association problem is equivalent to finding permanence of matrices. So that's kind of what it takes to compute the expectation. And of course, this is not a very simple problem. It's still sharp P complete, but there are a lot of polynomial time approximations to this that we can still exploit. And it's specifically in our application where we're detecting objects and images. We don't have that many objects. Maybe you have 10, 20, 30. The sizes of the matrices end up being 20 by 20, 30 by 30, so it's possible to still compute this. So our main result is something like this. The likelihood of these observations given the landmarks when the data association is unknown is proportional to some permanent of a matrix. So this is in the E step. So once we have this distribution over the associations, then we can do the optimization of the object positions and the sensor positions and orientations. So this part is a little more standard.
I'm sorry, excuse me,
yes.
but in order to get a square matrix, which you need for it to compute the permanent, you just add what the identity matrices in the corners?
Yeah, so you could.
Notation was?
Yeah, so you could actually, so the permanent is defined even for a rectangular matrix, but a lot of the existing approximation algorithms actually assume square matrices. So if you want to use one of the approximation algorithms, you want to, so what the identities mean here is like expanding the, if your bipartite graph is unbalanced, you need to add nodes that correspond to kind of imagine, so where did this measurement come from? If it's not from one of the landmarks, then it's from another node, which was clutter or some kind of false detection. So you need to augment the graph with these extra nodes which correspond to missing a detection or it being generated from clutter.
The notation is just those I sub.
Yes, so this ends up being like the identity and the matrix at once, exactly, yeah. Okay, so let's now look at the other side. So if we have a distribution over the associations, now how do we estimate the object pose? So we build, so here's an example. We have the camera observing an object at a certain time. We can detect kind of different parts of the object, like we said, wheels and windshield and doors and so on. They appear as these semantic features in the image plane. We can start to build a graph in which one node is the position of the sensor or pose of the sensor at this time, and then we have a bunch of nodes associated with each of the landmarks. So then if the camera and this observation provides some constraints among these variables. So if there were a movement, and we have an IMU measurement, this kind of introduces a new pose for the sensor in our graph, and there's another constraint given by the IMU observation. And then we have a second camera observation. This introduces more nodes and more constraints in the graph. So we end up building this large graph in which the nodes are variables that we're interested in estimating, the camera poses and the object features, and the observations are constraints, and they're given to us, and they're telling us kind of what are the values of the nodes, how close should they be. So in order to represent the objects, we introduce these constraints within the object itself, so we kind of know, so what is an object for us? So we represent it with its class, position, orientation, and also there are some constraints between its key points, so we know that, for example, the wheels shouldn't be very far apart from each other, or the wheels should be maybe under the doors or under the windshield, so we can add additional constraints based on this in the graph. So then the final problem ends up being something like a giant nonlinear least squares problem. So I'll skip a lot of the details, but so you have then, given the data association, you have an observation model for the camera observations, you have a model for the IMU observations, and then you have a model for the semantic key points now. So it ends up being something like minimize the sum over the errors in all the expected observations given the models, and then we can linearize this, turn it into a linear least squares problem, solve that, update our guess, and then repeat. So it ends up being something like solving this using Levenberg-Marquardt or Gauss-Newton method for nonlinear least squares. Okay, so I think enough on the math side. So let's see some examples now of why we spend all this time understanding the math behind it. So we can do things like this. So we can have a sensor moving around. Here are examples of these green points are the geometric features that we're detecting. We're also detecting chairs in this example, and the red points are the key points specific to an object. So we can use the geometric key points to estimate the trajectory of the sensor locally and optimize that, but not necessarily store them in a map or in a state. While the object detections we can keep in our state, and this gives us an estimate of the positions and orientations of the chairs. So in the end, we're able to get something like a map like this, which has like two different types of chairs and the trajectory of the sensor. So we can do this in, so here's another example with doors and chairs, and then I showed you earlier an example with cars. So some extensions of this work that we've been focusing on is how do we go beyond just points and orientations. We've also started looking at estimating shape as well, so we can represent the object with a mesh and then try to optimize the locations of the nodes on this mesh by comparing the projection of a mesh on the image to a semantic segmentation of the object. So if the mesh and the mesh projection and the semantic segmentation align well, we are kind of happy with the object shape. If they don't align, we can kind of compute an error, and then again we have a gradient that tells us how we should move the nodes on this mesh, and we can optimize the shape of a car. So this goes from something like a generic class model to something specific, like is this a Mazda or is this a BMW, or even in a manipulation problem that would be pretty important to tell exactly what does the cup look like and how should I grasp it afterwards. We've been thinking also about getting some uncertainty measures on the semantic side. So can I capture the variation on the semantic key points? So can I have an estimate of kind of how much they vary based on, so as we mentioned, these are detected using a neural network. So we're doing some work in Bayesian neural networks that can give us an estimate of the locations of the semantic key points. So at the end of this localization and mapping problem, we can build a map that looks something like this. So we have a bunch of objects, and each of them is associated with a Gaussian distribution over the positions and orientations, and maybe some kind of a discrete distribution over the class of an object. Is this a chair or a door or a table? Okay, so we have now this probabilistic description of the environment, and I want to go back to my original plan and now think about how do I generate trajectories for my sensor in order to minimize uncertainty in this map. So instead of someone driving the car around or someone joysticking the robot around, can the robot now decide how should I move in order to get the uncertainty in this map as low as possible?
Are you assuming that the objects are static?
Yes, so in a lot of what we've done so far, we've been assuming that the objects are static. So if you have a model of how an object moves, it wouldn't be hard to extend. But in a lot of situations, you actually don't know, right? There's people walking around or cars moving. So one idea is to start thinking about estimating those models online based on observations or based on the fact that you know it's a car. You so have some knowledge of the cars don't fly and they have some maximum velocity. It's something that we're interested in, but we haven't done yet. Okay, so I want to go back now to the original problem of how do we gather information. So given now we have a representation of the objects and the sensors and so on, we have this inference algorithm that can give us probabilistic maps. So how do I decide now a control policy for my sensors to minimize uncertainty, or in this case, entropy in the target states, in all the object states, given the observations over time, subject to something like the motion model of the robot, the observations, and this filter or this estimator that we just designed to estimate the robot positions and uncertainty will become one of the constraints in this optimization problem now. So the goal is to have something like this. We're hoping that we can have kind of a team of robots start to explore an unknown environment and detect all these blue points of interest, which again could be objects in the environment that you're interested in localizing well and minimizing uncertainty about. And then I want to be able to do this with a team of robots that can kind of collaborate and explore an area. So to understand this problem well, we first started looking at what is the simplest case where this problem makes sense. So the simplest case turns out to be if we assume linear and Gaussian models, what can we say then? So kind of going back to something like the LQR, LQG problem, but now our objective function is something different. So if we have a Gaussian distribution propagated over time, which actually is not far away from the truth, because for the object poses we do keep a Gaussian distribution, then the entropy in this state is proportional to the log determinant of the covariance matrix. So in the simplest case, we have something like the robot movement, something like the Riccati map that propagates the covariance distribution over time, and our objective now, instead of being linear, instead of being quadratic in the state and the control, is maybe this log determinant of the covariance matrix. So how do we solve this problem? So we could solve it either in continuous control space or in discrete control space. So we've focused more on the discrete side for a reason that with continuous optimization, you can only get local optimality. You can optimize kind of your trajectory to be very informative locally, but you wouldn't be able to do something like explore a space around different kinds of obstacles. So we've focused on having a finite control set. So how do we kind of generate finite different possible motions for our vehicles? So actually there's a lot of work in that. There's work in generating motion primitives for ground robots or for aerial robots or even for manipulators. And here's kind of some examples of controlling both a flying robot or a manipulator just using a finite set of motion primitives and then maybe even thinking about compositions around them, of them. So in our work, we specifically focused on doing this for a quadrotor. So for a quadrotor, we're kind of, what is the right way to discretize the inputs for a quadrotor? So a lot of the times if you ask someone that works in control, they're going to say, okay, you don't want to discretize things, but we can do it in a kind of a slightly more intelligent way than just blatantly discretizing the thrust and the moment for the quadrotor. The main idea we're exploiting is that a quadrotor and a lot of actually other dynamical systems are differentially flat. So what does that mean? It's kind of the output there's a set of flat outputs. So in the quadrotor case, it's the position and the yaw, of which if you take enough derivatives, so you have like the velocity, the acceleration, the jerk, maybe the snap, and then the derivative of the yaw, all these derivatives are enough for you to reconstruct the control input that would generate such a trajectory. So this gives us a way to actually rewrite, differential flatness gives us a way to rewrite the quadrotor equations into something like a fully actuated system, which is a very high order, maybe a fifth order fully actuated system. So how do we discretize the system? Now we can discretize the input for this fully actuated system. So in this case, it could be like discretize the jerk or the possible accelerations we can give for the quadrotor, and those then naturally generate possible motions in the lower derivatives. Like if I discretize the jerk, this gives me continuous acceleration, continuous velocity, continuous position, and so on. So we can start to build something like, here's a finite set of possible jerks. They generate some kind of a graph where the robot could move along, and depending on how finely I discretize, I can get more precise or less precise graphs. So if we're just thinking of a planning problem, we can use this idea of motion primitives to now actually kind of compose them and find the shortest path to a certain goal. But our ultimate objective is to find a path not that goes from point A to point B, but something that minimizes the uncertainty in the map representation. So here are some examples of kind of generating plans based on these discretized motions for a quadrotor to fly through an unknown environment. But here the goal is only go from point A to point B for now. And I want to get to the point where we're actually exploring and minimizing the uncertainty. So here's, because of the we have all the states, kind of the jerk and the velocity and the acceleration as part of the planning. We can actually optimize things like smoothness and also time it takes for the robot to get to a certain location. And for active perception, this is also pretty important because I want to be able to kind of control my robot in a way that I look at the environment exactly at a specific time from a specific point of view if I want to collect information about a process of interest. So here's a few more examples of kind of planning through cluttered environments and being able to pass through kind of holes that are potentially smaller than the radius of the quadrotor. So the only way you can do this is to actually exploit the dynamics of the robot and turn around to pass through this hole. And the way we are able to do this is by using these discretized jerk or acceleration spaces and the possible motions through there. So let's go back to the information gathering problem. Now if I have these possible different motions for my quadrotor, my problem ends up being something like this. I have an initial state for the robot, an initial uncertainty over the map. I can start to build this kind of a tree, which tells me if my robot were to go use this control input, I'm going to have this propagation of the uncertainty. If I use the second control input, I have a different propagation of the uncertainty, and so on. I can build kind of a tree of possible executions over time over which I can propagate the uncertainty in the environment. So if I were able to search through this tree, I can find an informative trajectory. But of course, the problem is that kind of the length of the planning horizon determines the depth of this tree. So if I want to predict what will happen in the future, the longer I want to predict it, the bigger of a tree I have. And then also the number of primitives I select determines the branching factor. So if I want to have more precise or more options for the motion of my quadrotor, then I have a bigger tree. So how do we search this efficiently? So it turns out that the problem is kind of hard as the planning horizon increases because the number of nodes here increase, and also if we consider multiple robots, the problem also becomes hard because then we need to think about kind of the Cartesian product of the control spaces for multiple robots, so it gets harder and harder.
Are you also, if you go back, are you also assuming that you know a priori, for example, all of the objects?
No. So far, I was saying we have an initial distribution over where the objects are, which would say something like you have an idea. But we can also do something like exploration where so the way we have done this so far is to have certain objects that do not actually exist on the frontiers of the map, and they kind of give you they kind of incentivize you to go there to minimize the uncertainty about these locations. So as you go there, your map frontier moves further away, and we can put some of these virtual objects which push you to explore. I think there are better ways of doing exploration, but that's what we've done so far.
Yeah, that's interesting, but what I'm saying is different. I just mean that sigma,
Mhm.
are the dimensions of it fixed?
No, so sigma can grow. So during the planning, during planning, we're assuming that sigma is fixed, and the way we apply this in a real system is actually we do something like open loop feedback control. So we first plan a trajectory, move for a little bit, and then update the estimator. Then sigma could change and grow, and then we replan. Yeah. So the way that we've done this is by replanning. Yes. So kind of the one extreme on this is to explore the whole tree. So something like forward value iteration does something like this. You get the optimal solution, but it doesn't scale at all. The other extreme that's very popular in practice is to do something like a greedy search where you only look one node ahead, you pick the best one, you commit to that, and then you continue this way. So this leads to linear complexity because you take a single path through the tree, but there's really no guarantee on how good your path is in the end. So what we've been interested in is, can we do something smart, something in the middle where we potentially explore nodes that are promising, but not all of them. So I'll skip a bit of the results here just to get to some more final results. But maybe our main result here is that we can actually identify a condition under which some of these trajectories are dominated by other ones. So in particular, if we have kind of several trajectories move in the same place in space, they would have kind of, depending on where the robot traveled to, they might have collected different information about the environment. So they might have different covariances associated with them, sigma 1, sigma 2, and sigma 3. So the main idea is that if it happens that they meet in the same place in space, and the covariance of one of them is larger in the positive semi-definite sense of one of the others, or a convex combination of the others, we can show that because of the properties of the Riccati map and the log determinant, that this trajectory will remain worse than the other ones for the rest of the planning horizon, because they're kind of in the same place. They have the same options going forward, which means that we can go back in the original tree and say, this node, which is dominated in this time, there is really no reason for me to explore its future evolution. So how do we identify these dominated nodes? We kind of solve this system of linear matrix inequalities to determine if a certain covariance matrix along a path is dominated by another one, and then we can remove all of these without affecting the optimality. Actually, we still find the optimal solution, and we can relax this even further. So instead of the trajectories meeting exactly, we can have like some delta close in space and epsilon dominated in information space. And based on this epsilon and delta parameters, now I can kind of control how I operate on this optimality versus complexity curve. On the one extreme where I don't prune anything, I still get the optimal solution, but it's very slow. On the other extreme, if I start to make this delta and epsilon very large, it's going back to the greedy solution where I only keep the best covariance, throw out everything. But we can operate in between. Okay, so we have some kind of guarantees on the optimality of doing this and how much loss there is. We show that the suboptimality gap is bounded regardless of the planning horizon and grows linearly in this epsilon and so on. So I'll skip some of the theoretical results. So again, the problem is hard because the planning horizon gets longer, and our answer to this was to identify these domination criteria and remove some of the dominated trajectories. We've also looked at doing this with multiple robots. Our approach there was to kind of decentralize the control, and we were also able to show that doing something like coordinate descent achieves at least 50% of the optimal solution because we have this information kind of measures, and they usually satisfy submodularity. So we have some results on the decentralized control, but I'm going over them quickly just so we can get to some more examples. So in the end, we can kind of use these ideas to do something like now autonomous mapping. So this is no objects here, but just a geometric map. But at every kind of point in time, we have a sequence of these possible motions. We evaluate the kind of the evolution of the covariance over them, and then we select the best possible trajectory to improve the map. And we can do this for a ground robot or for a flying robot. And again, we kind of plan, let's say, 10, 20 steps into the future. We select the best trajectory. We execute this for some time, update the distributions, then potentially the covariance has a different dimension, and then we replan a trajectory and so on. So we can do this also with...
So how do you, if you go back, so you're instantaneously planning to reduce the uncertainty in the map.
Yes.
But how are you encoding the state of each node in the occupancy map? Is there a finite number of states, like it's a
Yes.
wall or not a wall?
So it's yeah. So the occupancy map is kind of a grid of possible cells. Each one is either 0 or 1 occupied or free, and we have some distributions over this, like it's 50% occupied or 50% free. For the occupancy grid specifically, one way of doing this efficiently is to assume independence among the cells, and then the distribution over the whole map is just a product of the distributions of the individual cells. And then, so in this case, the distribution is not exactly Gaussian, because you usually use some Bernoulli distributions for the cells. So there are ways to do it with a Gaussian, or you can do it with the Bernoulli with assuming independence among the cells.
So why are you, okay, that was going to ask, why was the map not showing the probabilities? So
Oh, yeah, the map, this is not the probability, yeah, this is just showing the height, actually, the color.
Yeah.
It shows the height of the map. Yeah, that's a good point, yeah. I don't know why.
What was it showing? It was showing that.
The color shows height, so height of the map, so like brighter colors are just higher up in the z direction.
So that's just like the LiDAR data or something? Like what are you showing?
I'm showing the estimated map in which the color is just the z-axis. So if the color is red, it means it's the ceiling. If the color is blue, it means it's the floor. Yeah. It's not showing the uncertainty. That's a good.
But I don't understand how the estimated map has a resolution that's higher than the grid resolution.
Oh, it does not.
So you're showing just the measurements there, not the posterior.
So we're assuming that we're fixing the resolution of the grid, so we have a distribution just over this grid.
You have a grid on the screen.
Oh, I see. No, this grid on the screen is not the same. Yeah, that grid is just kind of the ground plane.
It's much smaller.
Yeah, the grid is much smaller than what's shown there. Yeah. Okay, yes, that grid is not the same. That's right. So here's kind of another example. We can do also target tracking, similar idea. We have these red targets. We might have some uncertainties over where they are, and then again at every time step we can plan trajectories which minimize the uncertainty over the targets, and then again assuming that we know how they move, we can do that, or if they're static, we can do that. If we don't know how they move, we need to estimate that, and we have not done this at all yet. So we can go beyond this kind of linear Gaussian and Gaussian distribution. So we've done some work in doing this for a camera by planning the trajectory of a robot arm that has a camera on its arm to kind of recognize objects. We've done also some work on recognizing objects by touching them, but the kind of the structure of the problem is pretty much the same. I have some distribution over the object shape, and I'm trying to, or the object class, and I'm trying to minimize the probability of error or the entropy in this distribution by choosing a sequence of grasps. So if they're stochastics instead of this deterministic tree that we showed before, we can do something like Monte Carlo tree search, where now our tree is stochastic, and then we have different kind of strategies of expanding this. So we can design a rollout policy based on the fact that we have an information measure again to guide the expansions or the rollouts in this tree.
So in this context, you're talking about the movements of the fingers?
Yes, so in the context of grasping, we're thinking about, so we have like 3 fingers. We can touch the object at different locations, and depending on where we touch the object, we get kind of an information of, so we are measuring something like the triangle and the tactile feedback around this triangle where the fingers touch the object. So we can plan the sequence of where to touch the object shape in order to minimize the probability of error, even classifying this object as, let's say, a bottle versus a cup.
Are you using vision at all? Or
No, so this was only with touch. Yeah.
Cool.
Yeah, so I think that's it. Thank you very much. I would be happy to answer more questions. Yes.
So everything you've done is like more of a traditional sort of mathematical setting, right? It's good, it's awesome, but the thing is, like, it can get super slow, right? Depending on how big your map is and things like that. Have you thought about like bringing in some deep learning to bring in like strong priors?
Mm-hmm. Yeah, so that's a great question. Yeah, so I'm very excited about using some of the learning techniques, but I'm always thinking a little bit, what are we trying to learn first? So for example, in the I understand a lot about the dynamics of my robots, so I don't think there's any point in learning the quadrotor dynamics because those are known and given. Things that could be learned that would be really interesting is to learn maybe the representation of the object. So instead of using these kind of semantic key points, what is the right way to represent an object? So what is maybe a way to compress an object, store it in my map, and then later on, this compression should be good enough to tell me what the object looks like again if I need to reconstruct it. Another idea could be, as you mentioned, for the map. Maybe in a navigation task, I don't need to build a perfect map of the environment in order to get to this door. So can I learn what are the relevant features, or what should I store in my map in order to be able to do navigation? So yeah, that's a very good question. We're thinking about how to use deep learning. Yeah, and we're looking at kind of reinforcement learning in which, again, the dynamics of the robot are known, but the representation of the environment or the cost function in the environment maybe is not known. And then another place is the Bayesian neural networks, where we can capture uncertainty over the predictions for the object classes, for example.
Thank you.
So what strategies have you thought about for the decentralized planning, where you have multiple robots sort of jointly trying to minimize uncertainty and selecting their future movements?
So far we have only one result on this, and let me go back to that. Sorry about that. Yes, so the main idea we had here was, instead of planning jointly for all the robots together, so that's the one extreme. The other extreme is every robot plans on its own, doesn't care about the others. We don't want that either. So our idea was to do something like coordinate descent, where the first robot plans on its own, ignores everyone else, but then passes its plan and what the evolution of the uncertainty will be along its trajectory onto the second robot. So now the second robot takes into account what the first robot is planning to do and then optimizes its trajectory. Then it passes the information over to the third robot. The third robot takes into account the first two and then plans its trajectory and so on. So this kind of sequential planning. And why this structure? So specifically, now the complexity becomes linear in the number of robots instead of exponential as before. Instead of comparing all the possible combinations of the controls for one robot versus another, we just do this linear pass through the robots. And as I mentioned, for things like conditional entropy or mutual information, those are submodular in the observations. So kind of as you're observing an object, if you see it multiple times, the amount of information you get decreases with every next observation. So seeing it 3 times, seeing it after having seen it only once, seeing it the second time is a lot more valuable than after you've seen it 100 times. The 101st time is not so useful. So based on this modularity, we can actually show that this coordinate descent gives us at least 50% of the optimal solution that you would get if you were to do it centralized, like plan for everyone. So that's the one result we have on distributed control.
So each robot only plans for itself.
Yeah, each robot only plans for itself. But the later robots, so there's some order, and the later ones already know how the previous robots are going to move, what parts they might observe. So now you know that, okay, my teammate is going in that corner to observe that part. I really don't need to go over there because he's going to reduce the uncertainty over there.
Shouldn't that result depend on the prior?
Should depend on the prior. So that's a good question. So I think, so here we are assuming that the estimation is still centralized. So everyone has the same prior.
So everybody coordinates?
Yeah, everybody coordinates in this.
The same initial estimate?
Yes, that's right. So we're distributing the control, but not the estimation.
Right. that may not always be.
Yes, so in practice that might not be true, right? If you have a truly distributed team, you have no way of synchronizing the map. So we have a separate result which is only on distributed estimation, no control. So we haven't put these things together yet. But it's a good, very good question, yes.
Well, but you could also, even if they had different estimates, you could first run a consensus algorithm. I mean, presumably you have some communication
Between the teams,
yeah.
yeah.
Bandwidth, then this assumption that you're making wouldn't be so.
Exactly, yeah. So if there's some way to kind of do, as you're saying, consensus over the distributions in the environment, even if they're different among the targets, if there's some way to do some kind of local geometric averaging, kind of like the consensus algorithms work, then.
Along the same lines, then you may be able to do the same thing with the control. So for example, if each robot planned for all the robots using its own information that it had available, then you ran a consensus on the control solution.
That's a good, yeah, we haven't tried anything like that. That's a good point. Yeah, the challenge with the control is that when you plan for multiple robots, it gets very expensive because they have many, many different options to consider then.
But I wonder if you can't take advantage of the notion that the robots that are trying to get this information are a team and assign a priori different roles to the members of this team.
Yeah.
That's actually much more legitimate than
That's a good,
prior information. And we know how to do that for things like soccer and, you know.
yeah, that's a good point. So something like looking at the current distribution, give robots certain areas. So you only focus here, and then they can plan in parallel.
Right.
It's a good idea, yeah. We haven't tried anything like this.